Okay, so we are going to start a new topic which is very natural extension of whatever we have done so far. It is joint and conditional distribution of random variables. So for that what we need a vector valued the notion of vector valued random variable. This PDF is already uploaded in your MS Team. You can download and see. Okay, so first of all, let us introduce the idea of vector valued random variables or random vector, sometimes also known as that. Okay, so technically speaking, that let omega a p be a probability space.
Sir, your screen is black.
But I have just restarted it. I have nothing more to do. I can, man. I have just restarted my computer. Is it blur for everybody?
Yes, sir.
Yes, sir.
Yes, sir.
But I have no other option. I have just restarted and entered in this. So let me just change the connection and see. Is it better now?
Yes, sir.
Yes.
Okay. So this is a probability space, and omega and omega is the sample space. Now you have x vector acting on omega, which is say x1 omega x2 omega, in this way say x n omega, n component vector you will get. That's why I have written as tilde here, x component omega. So that means this x vector, this is a mapping from omega to Rn. Technically, this is the thing. Now if you want to see examples, so let omega is your sample space, which is maybe the section 2, section 4 of PS course 20205, and each omega I is the ith student, then x1 omega I is the height of ith student, x2 omega I is the weight of ith student, x3 omega I may be male or female, x4 omega I is number of uh, brothers or sisters he or she has. X5 omega I may be the family income. So this is a very natural example. You can consider that your class is the sample space and you are one sample from that class, and as a consequence um, you can have this vector associated to you. Another example, you can consider, say, uh, this one. Uh, this is a very common example nowadays. Is it blurred again? Hello?
So sometimes it get blurred and for some time it gets clear.
Yeah, but it is now beyond my scope, man. I have just restarted the system and entered. What more can I do? If the system, I am using the LAN connection and
Sir, actually, when our internet gone weak, then it's happening.
okay. Anyway, let us see if, bear with it. Well, what can I say that uh, if now you may see it blur, but when you see the recorded video, it may be clear. With
No, sir,
that
even in
hope,
recording
let us
video, it is blur.
say again, please.
Even in recording video also it is blur. In the previous lectures when we watch, they are
Okay,
blur.
they are blur. Hmm.
Yes.
Then it is MS Team problem, which is beyond my scope. It is already now yeah. Sometime it is getting blur, and yes, I am seeing on my mobile screen also the same thing. Yeah, sometime it is getting blur and sometime it is coming back. Okay, let us see. How far? Now I think okay, right? Or got blur again? Hello?
Sir, it is
Yes.
okay now.
Okay, so let us continue. Okay, now another example, say for this one, that suppose nowadays people do lots of image analysis. So images are usually considered as a pixel grids, right? So in this way, maybe say handwritten image analysis or something like that, and there if you say have a number, say maybe written as with this three written. Now how you consider, so number of rows, number of columns, that many grid points are here. For each grid point you have some values, so you can stack this row 1, row 2 up to say row n. So first you write row 1 as a column, then row 2 as a column, row 3 as a column, row n as a column. So n many rows and maybe say m many columns. So this is a n cross m matrix, but this is a n into m dimensional vector, and you can go for the analysis of this kind of vector. So vector valued random variable is a huge application in statistics. Okay, so this is the idea. Now we need a probability distribution on it. So as usual we have to define the probability distribution. So let us define the probability. Where is black pen? Oh, no more black pen. Okay, so probability distribution of random vector. Usually we write in this way that f of capital X vector, small x vector, which we mean this intersection of all these probabilities, that probability x1 less than equals to small x1, x2 less than equals to small x2, in this way xn less than equals to small xn, where this here I should write this omega belongs to script omega, and this small x vector belongs to Rn. So this is the probability structure. Now we are going for a special case. First let us study about bivariate normal, bivariate distribution, and then in general we will see one extension with the multivariate normal in this course. So let x and y be a bivariate random variables. So if x y equals to probability x less than equals to small x, y less than equals to small y, where x y belongs to R, or you can write x y pair belongs to R square, doesn't matter. So it means probability of collection of all such omega such that x omega less than equals to x and y omega less than equals to y omega less than equals to y. And that means again probability collection of all such omega such that x omega belongs to minus infinity to x and y omega belongs to minus infinity to y, and as a consequence you have this probability of x inverse minus infinity to x, this set intersection y inverse minus infinity to y. This set probability of this entire thing. This is how, this is known as the joint CDF of x and y. Okay. This is in general true whatever may it be, and this joint CDF has few properties. So already you know the definition. Let us try to understand the properties. One, limit if I say x goes to minus infinity, sorry, minus infinity, and again simultaneously y goes to minus infinity, what will be the value of fxy? Can you recall the property of
0.
Yeah, 0, definitely, that is 0. Second thing, now take both of them to plus infinity, limit x goes to plus infinity, limit y goes to plus infinity, fxy, trivially this is 1. Okay, now one of them let us consider, limit x goes to plus infinity of fxy. Then what you are supposed to get? X takes all the possible values, but nothing told about y. So what will be the probability assigned to this limit?
The probability of y less than equal to y.
So this is p of y less than equals to y, and that is usually written as fy y. Similarly, limit y goes to plus infinity fxy, this is probability x less than equals to small x, it is usually written as fx x. So this is the marginal distribution of y, and this is the marginal distribution of x. So they are very much important aspect in this issue. Why marginal? It is called marginal. I will try to explain in a different way. For the time being, they are the names of being marginal. Now, the fifth property, which is equivalent to the property which is non-decreasing function. CDF is a non-decreasing function. So if we consider probability x greater than greater than a less than equals to b, and y greater than c less than equals to d, then how can you define this probability? And this probability is typically greater than equals to 0, that we all know, because it is a probability. So now this thing we can express in terms of CDF. How you can express in terms of CDF? So if you just consider, okay, so if you just consider this diagram, that maybe something like this, A to B, C to D. Okay, so these are the points. This is BD, this is BC, this is AC, and this is AD. Okay, so first you consider everything below BD. Okay, that means FBD. Then after that, so everything considered below this, then what you do, you subtract this section. Okay, so that means FAD. Then you subtract this section. So that means minus FBC. And that if you do that, you have subtracted this section below. twice, so you have to add that part f ac. Okay, and this quantity are both each of them are non-negative, and this entire thing is greater than equals to 0. So this is eventually representing the non-decreasing probability in 2 dimension. Non-decreasing property in 2D. Okay, now a special note that if you have x and y independent, if x and y are independent, then all of them will split as a product of the marginal probabilities that you know. So you will get this thing, probability A x less than equals to b, c y less than equals to d. You can write this entire thing in this way: if uh, if you can go by f of x and f of y. So f x, if I write f x b minus f x a into f y d minus f y c. Yes. So c to d, a to b. So in this way you will be able to split, because each of this term you will be able to split as fx b into fyd, fxa into fyd, fxb into fyc, fxa into fyc. So in this way, if you can split it, immediately you can have this product form. So that is the special case when x and y are independent. Otherwise, in general, this is true. Any query? Okay, so if there is no query, then good. Let us proceed, because many interesting things will be possible to do after studying this multivariate or bivariate probability distributions. Now let me jot down the two scenarios when, as of now, we have talked about a general distribution. Example, general distribution, you can see that the variables can be categorical, variables can be integer, variables can be uh, um, any real number. Okay, positive, negative, any real number. So all possible things can be there. So for the time being, we will consider only the discrete cross discrete case, or and discrete cross continuous cross continuous case. We preferably not go for much about discrete and continuous mixture, but some special cases we may consider in our problem session. So if x and y are discrete, then definitely what you have, that sum over f x y equals to 1, which is nothing but sum over probability x equals to small x and y equals to small y. This is the situation. And second thing, what you can have, sum over x fxy equals to f y small y. So marginal PDF of y. Similarly, sum over y fxy equals to fxx is marginal PDF, or sorry, PMF, you can write PDF or PMF of x, and this is fxy is the joint PDF or PMF, whatever you say, of xy. Now, if x and y are independent, fxy equals to fxx into y. So this is for the discrete case. Now similar thing will happen to the continuous case. If x and y are continuous, then the joint PDF you can obtain in this way: fxy equals to double partial derivative, you have fxy, and it is preferably assumed, need not hold always, but in this case del y del x fxy. So again similar result to this one, double integration xy fxy dx dy equals to 1, total probability 1. Second thing, the marginal, if you integrate over x, fxy dx equals to fyy. Third thing is integration over y, fxy dy equals to fxx. And as a consequence, again, if x and y are independent, then f of xy equals to fxx. So these are the thing in general true, no specific example I am going for. Now I will go for example, and rest of the thing will be the consequence of this example. And so any query with this few introductory thing? Okay, now you look at this example very carefully. So suppose you have uploaded two videos, related videos, and in YouTube, and you are trying to see the, okay, so and you are following the number of uh, observer who have watched both of the video and given their like and dislike to in that way. So, and you want to see the distribution pattern of them. So I am just trying to model that thing here in this way, that you have video 1, video 2, video 1 liked, video 1 disliked, video 1 liked, video 1 dislike, video 2 like, video 2 dislike. So video 1 like, video 1 dislike, video to like, video to dislike. Okay. Now, say for example, video 1 like, probability of liking video 1, probability of like video 1 is say P1, probability of dislike video 1, let us call Q1. Similarly, probability like video 2 is P2, probability dislike video 2 is Q2. Now suppose for the time being that these events are independent. Okay. Now what will be the probability that video 1 like, video 2 like? Both, one person who has watched both of the video, he will like the first video and the second video. If they are independent, then what will be the probability?
P1, P2.
P1, P2.
P2 or P1, P2. Okay, so what will be here? Video 2 like, video 1 dislike, Q1, P2. Now similarly here it will be P1, Q2 and it will be Q1, Q2. Okay. Now if this is the setup, what will be the probability of video 2 like? If you take the row sum, what you will get?
P1 plus Q1, P2.
Yeah.
P1, P2 plus Q1, P2.
Yeah. So what will be the total sum? What will be the relation between these two?
Equal to 1.
Sir, but we cannot say is equal to 1 because somebody neither likes nor dislikes.
No, I am saying that whatever observation you have got, if somebody doesn't give any response, you cannot control that thing. Only you are tracking those person who have given response for both of them.
Okay, sir.
Okay. So now you can see that if you do this row sum, you will get P2. If you do this row sum, you will get Q2. If you do this column sum, you will get P1. If you do this column sum, you will get Q1. Now you can see that the probability distribution of video 2 is in this margin. Probability distribution of video 1 is in this margin. So that's why the term marginal distribution has come. Okay. So marginal distribution, this term has come eventually because of this kind of structure. You can have the probability in a tabular form, and in each of the margin of this table you will get the marginal distribution if you take the row sum or the column sum. So that's why the term marginal distribution has come. Now if you assume that they are independent, you have seen this thing, but if I add some small number, very small number to each of these cell such that the marginal remain unchanged. So I am adding plus epsilon, it is still become a valid probability to keep the marginal value unchanged. What I should add here?
Minus epsilon.
Minus epsilon. what I should add here? This margin unchanged. What
Sir,
adjustment?
minus epsilon.
Again minus epsilon, and here I should add plus epsilon. Okay. So epsilon is a positive number such that probabilities are valid. It should not go such a negative number that probability is not valid or it will exceed 1, not such number. Now you can see that with this structure, if I say that like is 1 and dislike is 0 as you define the random variable. So probability, what should I say?
Sir,
Okay,
epsilon
so
can be less than 0 also.
epsilon can be less than 0. Of course it can be. You have to define in such a reasonable way. Yes, it can be, of course.
Okay, sir.
Because if you take this is negative, then this will be positive. It doesn't matter too much. Okay, so if you denote the random variable associated with video 1 is x and random variable associated with video 2 is y, then probability x equals to 1, y equals to 1 is P1 P2 P1 into P2 plus epsilon, which is not equals to probability x equals to 1 into probability y equals to 1 when epsilon is strictly greater than 0. If it is, I can write in general. So if it is exactly equals to 0, then they are independent. If epsilon is greater than 0 or non-zero, then they are dependent. So what is the conclusion from here? Can you tell me?
X and Y are not independent.
Yeah, x and y are not independent, that's all right. But for how many values of epsilon such a condition can hold that the marginals are unchanged, but their dependency can be different? So if I say, for example, if I choose epsilon as 0.001, there will be a certain level of dependency. If I choose 0.005 within valid range, 005, then also there will be certain dependency. Whatever may be the number you choose within possible range, your marginals are still unchanged, but your dependency are going to be changed. So the conclusion is this: even if we know the marginal distribution of x and y, we may not know the distribution of x, y jointly. May not know. If you know the marginals, it doesn't guarantee the joint distribution. But if we know the joint distribution of x, y, then we always know the marginal of x and y. This is the fundamental difference. Is the point clear? Anybody has any query? This is a very fundamental thing. And this particular model is one of modeling. There are many other ways, but this is one of the particular modeling of bivariate Bernoulli random vector. Probably you will not get this example in your usual textbook. So this is first time I think introduced in 2007 this model, and then it is implemented and some research work has been done. There are many bivariate binomial, there are many more than one models for bivariate. You can sum this kind of vector and you can have bivariate binomial, but bivariate binomial can be defined in many different ways. One of the way is you consider this kind of variable and take their sum, as you have done bivariate Bernoulli distribution. Some of them is binomial. The same extension is possible for this one, but the other structures are not so simple. So this is one example, and you remember this example. This will be a special example what we will come back in future. Okay, so if there is no query, let us proceed. The conditional PDF, it is now you are entering in the most interesting part of probability, and that is the conditional distribution. And many difficult problem can be sorted out very easily if you have certain level of mastery with this conditional probability distribution. Okay, so the conditional PDF or PMF is defined as follows. So the conditional density of Y I am writing density in general. So you consider either PDF or PMF, whatever may be, of Y given x equals to small x is defined as in this way: f of y given x, that is y given x equals to small x. Sometimes it is written only small x, sometimes written x equals to small x, so they all mean the same thing. It is the joint density f of xy or joint PMF divided by the marginal of x when f of marginal of x is strictly greater than 0. This is the definition. Okay. You never say that this is the probability. This need not be the probability. This is the joint density. This is the marginal density, or joint PMF divided by the marginal PMF. If you are dealing with discrete valued random variable or discrete random vector, then it will be probability. If you are not dealing with discrete random variable, this will be in general the PDF, marginal PDF. So in general, whatever we have written here is the marginal PDF or PMF, here is the joint PDF or PMF. So don't get confused that this is probability, this is probability. That is not true. The truth is this is marginal density of x in terms of PMF or PDF. This is joint density of x and y in terms of PDF or PMF according to they are discrete or continuous, whatever may it be. So this is marginal PDF or PMF. This is joint PDF or PMF. Probability interpretation is valid when x and y are discrete, otherwise not. Be careful. Students often do this mistake. They say this is probability, this is not probability. Probability interpretation only gets restricted with the marginals of a discrete valued random variable. Otherwise, in general, they are true. Similarly, you can define probability of y given x or x given y. There is no harm in it. Okay, so now we are going to study few laws of expectation which are very important, that we have stated and taken for granted for our course, and we have calculated all the mean variance stuff in our previous section. Now the time has come that we will prove all this, or at least whatever necessary that. So properties of expectation. Okay. So as you know that when we define expectation, we first consider their absolute convergence. So for this kind of work, we assume that expectation of mod x is finite, expectation of mod y is finite, expectation of x squared is finite, expectation of y squared is finite. This is the thing for say joint PDF x and y, or joint PMF x and y, doesn't matter. So now we want to show that expectation of x plus y equals to expectation of x plus expectation of y. This we have used it, but we have not proved it. So first of all, what you need to check that whether this is finite or not. Expectation of mod of x plus y, and so you can consider this quantity as, I am going by the continuous notation, double integration x and y, x plus y mod fxy dx dy, and then you can go by the triangular inequality, double integration xy mod x plus mod y fxy dx dy. Then you can split it by the Riemann property, in double integration mod x fxy dx dy xy plus double integration xy mod y fxy dx dy. Now here x is there, y is not there. So if you take the integration first with respect to y, then you will be left with x mod x fxx dx plus y mod y fyy dy. Now you can see that this quantity is nothing but expectation of mod x plus expectation of mod y, which is assumed to be finite from these two things, and as a consequence this quantity is finite. Okay. Now as expectation of mod of x plus y is finite, define expectation of x plus y is equal to double integration x plus y fxy dx dy integration, and that thing if you again split it and do this all similar kind of work, now equality will hold. You will get expectation of x plus expectation of y. The most important thing here is this will always hold. Expectation of x plus y equals to expectation of x plus expectation of y. Independence not needed. Whether they are dependent variable, independent variable x and y, it doesn't matter, this result will hold. And in general this will hold. Expectation of ax plus by equals to a into expectation of x plus b into expectation of y. So in general this will always hold. It doesn't matter independence is there or not there. You need not worry about the sum law of expectation will always hold. So this is known as the sum law of expectation. Okay, but the product law of expectation will not hold until you get independence. So let us go for the product law of expectation. So let x and y be independent. That means fxy equals to fxx into fyy. Okay, this thing holds. Then what you need to do, you need to show that please mic out. Expectation of xy equals to expectation of x, expectation of y. Again you have to do the checking whether it is finite or not. So first you need to consider expectation of mod of xy. So it is again expectation of, so you can write double integration xy mod of xy fxy dx dy. This is trivial. So you can use this property here, double integration xy mod of xy fxx fyy dx dy. So you can split separately fxx dx integration y f y dy. So it is expectation of mod x into expectation of mod y. which is finite by the assumption, general assumption that we have made. Now, as they are finite, define as expectation of mod of x y is finite, define expectation of x y is double integration x y sorry x into y fx y dx dy, and again do the similar job. Equality will hold everywhere, so you will get expectation of x into expectation of y. But here independence is must. Without independence you will not get this thing under independence. Now here I can give you few homework which will be useful. Let us. Okay, so one thing you try to do this homework, that if expectation of mod x to the power, have I told it, r is finite, then expectation of mod x to the power s is also finite when r is greater than s. Okay, prove this. This is one interesting fact, might be often useful. Another fact, let us define covariance and then we will talk about it, because covariance is another important aspect what we need to cover. 5, 6. Okay, so covariance between x and y. Here another game, new game starts. The covariance between x and y is defined as, in this way it is written, cov of x comma y is expectation of xy, sorry, x into y minus expectation of x into expectation of y if exists. That means each of these term exists in the sense of absolute convergence holds. Then you can also express this quantity as expectation of x minus expectation of x into y minus expectation of y, this thing, and you can see this is also covariance of y and x. So it is symmetric. Symmetric function of y and x. Now, can you please tell me what will be the covariance of x and x? If I write covariance of x and x, what will be its interpretation?
Variance of x.
Yes, correct. It is, you go by this one, this line, then it is expect, or this line, whatever, expectation of x minus expectation of x whole square. So this is variance of x. Okay, so usually the bivariate or multivariate random vector, usually this is written as the dispersion matrix. So D of, maybe say in this way, x y vector, which is variance of x, covariance of xy, covariance of xy or yx, and variance of y. And sometimes it is also written in this way: sigma x square, sigma xy, sigma x y, sigma y square. Another notation is also useful, that sigma xx, sigma xy, sigma yx, sigma yy. So if you write this quantity as sigma xy, then it is same as sigma yx. Yeah, no. Anyway, you can understand this. The covariance of xy. So this, whatever, either this notation sometimes follows or this notation follows, this notation followed, you have to understand from the context. So sigma xs, eventually here it means sigma x squared. That means the variance. Sigma yx is same as sigma xy. Okay. So now if you consider that covariance as we have defined, so now let us call for a situation that what will be variance of ax plus by. Expectation we have just seen. Now let us talk about the variance of this kind of situation. Variance of ax plus by. If you go by definition, what are the things you will get? Can you write this thing in this way? Covariance of ax plus by and ax plus by. Can I write following this? Is it okay for everybody?
Sir? Yes, sir.
Okay. Now break it and take turn by turn. Covariance of ax plus covariance of ax by plus covariance of by ax plus covariance of by. Now, can you please tell me what will be this one?
Variance of x.
But what happened with a?
A squared
A
variance of
square.
x.
A square times variance of x. What will be this term? Look at this expression and quickly tell me. Use this property, that expectation of ax equals to a into expectation of x, which is trivial to note. What will be covariance of ax by?
Sir, A into B covariance of x.
Perfect. Similarly, it will be A into B, again covariance of xy because they are symmetric, and it will be B square variance of y. So now you know the general formula. This is A square variance of x plus B square variance of y plus 2 times AB covariance of xy. Got it? Now I am trying to tell you another general form here. So if I call this matrix as say D matrix, this any of these matrix, whatever you say, then can we write in this way D AB AB check, AB as a column vector, AB as a row vector. Will you get this thing? Is it okay for everybody? 2 cross 2 matrix. So this quantity is sigma xx.
Yes, sir.
This is sigma y y. This is sigma xy. And again, this quantity ax plus by, this is eventually can be written as, this is variance of a b vector, I mean this is a row vector and xy vector, column vector, dot product. That means ax plus by. That is what we have started with. This general notation is readily extendable for n dimension. So if you have a1 x1, so a2 x2, a3 x3, an xn, and you have given their variance covariance matrix. So this is known as the, this is dispersion matrix or variance covariance matrix. So usually when you go for say high dimensional data, you will have this variance covariance matrix, and if you need to study their linear combination like this a1 x1 plus a2 x2 and a3 x3, you can immediately do in this way, write the dispersion matrix in the middle, whatever the coefficient vectors you have, you write in front as a row vector transpose as transpose, and at the end as column vector. So you will have an expression that will be the variance covariance, that will be the variance of the linear combination all those vectors. So this is a very general idea. In higher dimension, you preferably use this kind of thing. Writing this way is become much more cumbersome. We use the matrix representation in this way. So this is row, this is column. Their dot product is the linear combination. Their variance, you can write the variance covariance matrix in the middle, the column vector at the end, row vector in the front. You do the multiplication, all will be in one go. Okay, so we have got the covariance structure, variance covariance structure at the same time. Now we will see an interesting concept which is known as the marginal or expectation through conditional expectation. This is the key tool. Okay, if you really want to become a master of probability, this tool you have to learn with a great interest as well as great depth. So expectation through conditional expectation. Okay. So first of all, let me define what is conditional expectation, then we will define what is expectation through conditional expectation. So the conditional expectation of y given x, so this is very, very important. So the conditional expectation of y given x is defined as expectation of, assume everything exists, y given x equals to small x. In this way you can write, that is integration over y, small y, conditional distribution of y given x dy. Okay. So because wait. Yeah, so dy, and that means here x, small x is fixed and it will be a function, hence it will be function of x. This quantity will, you will do the integration with respect to y, it will be left with this small x, so it will be a function of x. So if you even split it, y fxy divided by fxx dy, or if it is discrete, then sum over y fxy divided by fxx. Okay. Interesting fact, let me just tell you here that this thing, expectation of y given x equals to small x, this has a special name. Do you know? You have heard it, but probably you don't recognize. This is known as the regression function of y on x. This is the definition. This is the definition of regression. And this, it is also true, all of your seniors are doing similar mistake, that when the definition of regression is asked, they start with an example, and eventually that is a special case, not the definition. The definition of regression is this, that the conditional expectation of y given x is known as the regression of y on x. If you go the reverse way, expectation of x given y, then that will be the regression of x on y. So this is the definition of regression. So first we have defined the conditional expectation. Now if we want to know the unconditional expectation of y, and if we want to get that thing through this conditional expectation, how we can get, let us do that, because that is the thing will help us to solve many problems very easily. Okay, so yeah, now 6. The conditional expectation through a unconditional expectation through conditional expectation. So the unconditional expectation with respect to conditional expectation. Okay, so suppose we are interested for the unconditional expectation of y. Okay. Now this thing I can split and convert it to a conditional expectation and then take another expectation over which we are doing the conditioning. So it is like a compound probability calculation. Instead of probability, you are calculating expectation. So it is, you can write this thing in this way. Every time you fix one value of x, calculate the expectation, it will be a function of x, then that function you take the expectation. So in that way it will work. So how the formula will conclude? So let us try to write it down. So if you start from the right hand side, so this part is a function of x. So if you start with the right hand side, so it is expectation of x, then expectation of y given x, y given x, I can write in this. Now if you go by definition, this part already you have seen that how you can write this conditional expectation. I am going by this notation. So this quantity is integration over y f of y given x dy. Okay. Now if you now compose expectation of x on it, so integration x integration y f of y given x into f of marginal of x dy dx. So x y f by definition of this fxy fxx into fxx into dy dx. Now you can see that fxx and fxx, they eliminate each other. Double integration xy y f of xy dy dx. So now if you integrate with respect to x first, then you will get y f of y dy y. So this is nothing but expectation, and this makes our life much more easy in many situations. We will come across the examples later on, but this is a very fundamental tool and you have to have a strong hold on this result. I am giving this one as a homework, which is something little bit interesting. Variance of y, you can also express in terms of conditional variance, is expectation of x, expectation of y given x of y, sorry, I have done a mistake. Variance of y, you can split it into two parts, EV plus VE. It is often known as EV-VE formula. So here you first at the outer side you consider the conditional thing, y given x, and here you take the marginal, y given x, here you take the marginal. So this is not one term as you have seen here. Here expectation of x, expectation of y given x, it will become expectation of y, but here you have two terms, EV plus VE. So you try to prove this one and you notice this thing, this is expectation of variance, which is a non-negative quantity, variance of expectation, which is also a non-negative quantity. Okay. So variance of y is always greater than equals to expectation of variance of y given x. Okay, and this is the thing what you can see here, this expect and also variance of y is greater than equals to variance of expectation of y given x. Both of the term is less than the this one, less than equals to, you can say, but this one has an interpretation. Expectation of y given x, this is regression, this part only. So the variance, if you do unconditional variance, is more than the regression variance. But anyway, regression is not a part of your course. When you, if you take the regression course and if I teach, I will come go in details of all those stuff. I will then check how many of you remember the definition of regression there, because many students take regression after doing this probability. This semester 175 students are doing. Okay, so this is the conditional expectation, conditional variance, all those stuff are done. Now we are going for another important aspect which is very often used and very often misused. So let us talk about the correlation coefficient. Correlation coefficient. Correlation coefficient is defined in this way, usually written as CORR or COR, doesn't matter, x and y. This is covariance of xy divided by square root of variance of x into variance of y, if all those terms exist. So again, it is expectation of xy minus expectation of x into expectation of y and square root of variance of x into variance of y. So in short, you can also write sigma xy divided by sigma x, sigma y. In this way also you can write it. Now the property A is, if x and y are independent, what will be the value of correlation xy? Can you quickly tell me?
0.
0, as covariance of xy is 0. It is 0. B, if correlation of xy equals to 0, will it imply they are independent? Is the reverse true? If correlation is 0, will it be implying that x and y independent? Okay, so in general it doesn't imply. In general, The special case we will come across, correlation coefficient of x and y, absolute value of that is always bounded by 1. And last remark is correlation coefficient or correlation of xy measures linear dependency between x and y. So it can measure only the linear dependency. It cannot measure the, if there is some nonlinear dependency is there, correlation coefficient cannot measure. So eventually what we want to see, if x is increasing, whether y is increasing or not, if x is decreasing, whether y is decreasing or not. That is the thing we can easily see. But if there is some nonlinear type of dependency, the correlation coefficient cannot measure it properly. Now I am giving a counter example of this situation, where example when correlation xy equals to 0 implies independence. We will prove this thing also. So example 1. Okay, so you come back to this one once again. This situation. Can you please tell me that what will be the covariance of xy? So that I can write it here. So consider bivariate binomial situation, whatever you have studied, bivariate Bernoulli. And covariance of x and y. What will be the value? To go by the definition, expectation of xy minus expectation of x into expectation of y. What is expectation of xy?
P1, P2 plus epsilon.
P1, P2 plus epsilon is the covariance, minus covariance of x.
P1.
So expectation of xy is this, minus expectation of x is P1 into expectation of x is P2. So covariance is epsilon. Is it okay? Covariance is epsilon. Yes. Yeah, very easy. Now if epsilon is 0, so covariance is epsilon, correlation will be some variance divided, no problem. But if epsilon equals to 0 implies covariance of xy equals to 0, and that implies what you have already seen, that if epsilon equals to 0, then probability of x equal to 1, y equal to 1 equals to P1 into P2. Independence implied. Is it okay? If epsilon is 0, this equality will hold. If epsilon is not equals to 0, this equality will not hold. And epsilon equals to 0 means covariance 0, and here covariance 0 is implying independence. So this is one example. Another example, we will not go in details today. I will share you one recorded lecture, because I will not be able to take class in coming 2 Mondays. So I will share you a 2 hours lecture video for these coming Monday and the next Monday, before puja and after puja. So there you will get all the details of bivariate normal distribution. So if we the bivariate normal distribution x y, it is denoted in this way. You will see that mu x mu y, that is expectation of x, expectation of y, sigma x square variance of x, sigma y square variance of y, and rho is the correlation. So usually this is denoted by rho. Now for this case, rho equals to 0 implies independence. This proof you will see in the next lecture. So usually these are the two very common and easy example where correlation 0 implies independence, otherwise in general they don't imply independence. Now we will look into these properties one after another. Okay, so now let us try to construct this example that correlation 0, correlation xy equals to 0 doesn't imply x and y independent. Okay, so let us see this one. Okay, fine. So now let us consider x is following uniform -1 to +1. Very simple density I am taking. So it is symmetric around 0. Note this thing. And y given x, I am fixing the conditional density. Y given x, you choose x from here. Y given x is again following uniform x square minus 0.05 to x square plus 0.05. Okay. So what will be the covariance of xy? Go by the definition. Expectation of x into y minus expectation of x into expectation of y. Okay. So what you know, that this quantity will be 0. Expectation of x is 0 because it is symmetric around 0. So it is expectation of xy. Now expectation of xy, now you will see the application. You can go, this expectation you can calculate through conditioning. So let us go by that. Expectation x, expectation of y given x. Now this x is fixed, x into y. So you can write in this way, expectation of x, x into expectation of y given x of y. Okay, so from here, this is the conditional distribution of y given x. So what is expectation of y given x? Can you quickly tell me?
X square.
X square. So this is expectation of x into x square. So it is expectation of x cube. Now x follows uniform -1 to +1. What will be the expectation of x cube?
0.
0, because it is an odd function. Symmetric odd function 0. Now you can see that although there is a quadratic relation between x and y, covariance of xy equals to 0, that implies correlation of xy is also 0, but correlation 0 doesn't imply that they are independent. Already dependence we have constructed, but still we are ending up with correlation 0. So correlation 0 in general doesn't imply they are independent. So if you want to draw the region where this density will lie, you can draw in this way, that this is some point like this. So here it is 0, and you can consider that this is from -1 to +1, and for each of the value x you have x square. So this is minus x, that is also x square, this is plus x, that is also x square, but around x square there is a region with -0.5 to +0.5, so it's a very small region. So for each of them like this, so you will have a band like this and a band below also like this going. So within this shaded region all the xy values will fall. Okay, so I should, this part will be a straight line, this part. So within this shaded region this xy will fall, and this is a special case when correlation 0 doesn't imply independence. Okay, now we are going to prove the very important property that that the correlation lies between -1 to +1. Okay, so let us do it. We need page. Okay, so to show correlation of xy lies between -1 to +1. Okay, so let us consider in this way that let z equals to x minus expectation of x, w equals to y minus expectation of y. So from here you can immediately see that expectation of z equals to 0 equals to expectation of w, no harm in it, and variance of z equals to variance of x, at the same time variance of w equals to variance of y, no problem with it, a very simple observation you can do. So showing this thing is equivalent to show this thing, that covariance of xy divided by mod square root of variance of x into variance of y less than equals to 1. So that is equivalent to show covariance of xy square less than equals to variance of x into variance of y, and that quantity is again eventually showing that expectation of x minus expectation of x into y minus expectation of y, this quantity whole square less than equals to variance of x into variance of y. Then again you go by this notation, this is eventually same thing, is expectation of zw whole square less than equals to, I can say, variance of z into variance of w, and expectation of z is 0, expectation of w is 0, then it is also equivalent to show z expectation of zw square less than equals to expectation of z square expectation of W square because their individual expectations are 0. Okay. So this is what we want to show finally. So we need to show this. Okay, now let us define T, another random variable which is again a linear combination of Z and W in this way, Z minus lambda W, okay, with real lambda, where lambda is real. Okay. Now, what will be the expectation of T? What will be expectation of T?
Sir, expectation of Z minus lambda times expectation of W.
And you know this? Now you tell me.
0.
Sir, 0.
0. Okay. Now, variance of T is expectation of T square. Do you agree?
Yes, sir.
Do you agree with it? Because expectation of T is 0. So this quantity is expectation of Z minus lambda W whole square. Sorry, expectation. Okay. And this quantity is expectation of Z square plus lambda square W square minus 2 lambda Z W. Okay. Just I have expanded the square term. Now you take it term by term, expectation of Z square plus lambda square expectation of W square minus 2 lambda expectation of ZW. Okay. What we can claim that as it is a variance, this quantity is greater than equals to 0 as it is a variance. It is a variance of T. Finally, this expression is greater than equals to 0, and this expression I am writing as Q lambda. So it is a quadratic expression of lambda. Okay. So now let us focus on Q lambda. So Q lambda, which is lambda square expectation of W square minus lambda into 2 times expectation of ZW plus expectation of Z square. This is greater than equals to 0. So this is what you know. Now you tell me that this quantity, when this quadratic expression is taking value greater than equals to 0, what will be the condition of their roots? Their roots will be real or imaginary?
Either equal or imaginary.
Say again, please. Either equal
Either
or imaginary.
or
Okay.
imaginary.
Yes. So uh, Q lambda equals to 0 will have either equal or imaginary roots. Okay, so what will be the condition for that?
Discriminant is less than or equal to 0.
Which one?
The discriminant of the
Okay, yeah,
b square minus 4ac should be
b
less
square
than or equal
minus
to 0.
4ac. Okay, so tell me what will be b square? B square, this is b, right?
Yes, sir.
So 2 into expectation of z w whole square minus 4 times a is expectation of w square, c is expectation of z square. This quantity is less than equals to 0. So that implies expectation of ZW's whole square less than equals to expectation of W square expectation of. Check. This is what we have wanted to show. Okay. So hence the proof. So this is greater than equals to 0, that implied and implied by this is implied and implied by this. And that eventually means this thing, that the covariance of x correlation of xy is bounded between -1 and +1. So this is the proof. And okay, so let me, as we are doing this thing, let us say again. So if you, when the equality will hold? When the strict equality will hold, either it is +1 or -1. So this is eventually saying the same thing, is that covariance of xy square is less than equals to variance of x and variance of y. When the equality will hold. Here you can say, or here you can.
Sir, when there exists a lambda such that t is identically 0.
Okay, so that means equality will hold when z equals to lambda w, right?
Yes, sir.
Yeah. So that means x minus expectation of x equals to lambda times y minus expectation of y. Okay, that means x, or okay, so you can write in this way, that x equals to expectation of x minus lambda times expectation of y plus lambda times y. Sorry. So you have this structure, x equals to a plus by. Okay, so that means a x and y are linear in relation, exactly linear in relation. So if you have x and y exactly linear in relation, then you will have correlation either +1 or -1. Very easily you can check that covariance between x and y equals to uh, covariance between, I can write x as a plus by and y, so which is nothing but b times covariance of y and y, which is b times variance of y. And what is the correlation between x and y? It is covariance of xy divided by square root of variance of x into variance of y. So from the formula here in numerator you get b times variance of y. Here what you get, variance of y as it is, variance of x. Variance of x is nothing but b square times variance of y. So it is b times variance of y divided by mod b times variance of y. So it is b by mod b. So it is the sine of b, which is +1 or -1. So the correlation becomes +1 or -1 if they have exactly linear relationship. Okay, good. Now quick problem time. Just before leaving, I will solve few more problems when I will start the class again. But before that, you better to listen that recorded lecture that I will share itself today. Before we leave, let us ask a quick question. Example. Okay, a coin is tossed n times. X is the number of head obtained, y is number of tail obtained. What is the correlation between? That's a very important interview question. Very easy question. You tell me. A coin is tossed n times. X is the number of head obtained. Y is the number of tail obtained. Nothing told that fair coin, unfair
-1.
coin. P lies between 0 and 1, open interval. Okay, so P lies between, probability of head equals to P lies between 0 and 1, open interval. That much needed. Nothing more told. Tell me, what will be the answer?
Sir, -1.
-1, correct. How?
Sir, y
X
equals
plus y
n
equals
minus
to n.
y.
Yes, y plus x equals to n. So you can write it as y equals to n minus x. And variance of, what is variance of y?
n into 1 minus p.
N into p into 1 minus p, and same thing as variance of x, n into p into 1. So it is minus 1. Okay, thank you. Enjoy the puja vacation, stay safe, and if the exam for other slot A is over, we will try to share the answer key. You get back to us as early as possible, and then we will go for the evaluation. Hope there was not much trouble in your exam yesterday, technical or medical. Few response I have got. We will take care of that definitely. Okay, so all
Thank you,
best
sir.
wishes for your puja.
Thank you,
Yes.
sir.
Yeah.
Thank you, sir.
Stay safe.
Thank you,
Do
sir.
enjoy it, but try to stay safe and avoid the crowd. Thank you. See you after puja. So this coming Monday and the Monday just after puja, I will not be able to take the class. Today itself, I will upload these notes and the video lecture for 2 hours for 2 Mondays, and then when we will meet there will be one holiday on Tuesday, so that lecture will be also gone. So we will miss 2 hours class there also. But anyway, we have covered enough today. So when the next I will take live classes, whatever you have queries related to the recorded video lecture and today's lecture, we will sort it out, and one very important transformation we will see in that example, which will be used for statistics part. If we cover it here, good, not maybe in the regression course it will be used. Okay, see you. Thank you.